So we're going to try to figure out what the A, the P, and the Q do, and we're going to go to Desmos and start off with just y equals x squared. So there's our x squared graph. And the first thing I'm going to try to figure out is, what does the P do? So I'm going to go here and I'm going to go minus P, and Desmos is really cool because it says you want to add a slider. I'm going to go yes, and let's go steps by one. We're going to start with P equals 0. Well, there it's equal to 0. And if I make P equal to 1, it moves it 1 to the right. If I make P equal 2, it moves it 2 to the right. 3 moves it 3 to the right. 4 moves it. And you can see that you can move your graph left and right depending on what your p-value is. Now, if I make p equal to 6, your equation would be x minus 6. So when it's minus 6 in the equation, your vertex is at positive 6. Because it's really thinking what x would still make it 0. It would be a positive 6 that would still make it 0. So we saw that the p-value moves things left and right. Next, I can add my q and add a slider for that. Jump by ones again here. Perfect. Jump by ones here. And we noticed with the q value that if you go plus 1, it moves it up 1, plus 2 moves it up 2, plus 3 moves it up 3, plus 4, plus 5, plus 6. Uh-oh. Plus 7 makes it disappear. No, it's just too high. It's not, there it is again. Don't worry. And if you went negative, it goes down, and so on. So you can find the vertex of your equation, because if I would go up 2, and then I go to my p-value, oh, that's not what I wanted to do. There we go. Oh, this one. Right? If I had my p-value at 4 and my q-value at 1, my vertex is now at 4, 1. Then we added a number in front. I'm going to move this one back to 0, this one back to 0. So there's a regular parabola. What happens if I change the a value? Well, as a got bigger, I wonder how I could use my arrow keys. Oh, I did it again. Struggling a little bit. Keep accidentally erasing it. Oh, but then, look, as a gets bigger, do you see that your graph is getting narrower and narrower and narrower? And as a goes to the negatives, well, that flips it upside down and it opens down. And if I go into fractions, if I go 0.1 here, if I go less than 1, it gets wider. So when it's between 0 and 1, it's wider than x squared. Here's x squared. And when it's bigger than 1, it gets narrower. So putting these things all together is our strategy for graphing and understanding functions. So what we're going to do is we're going to go to the construct the understanding at the bottom. And I would like you to quickly write down the vertex for all 7 of these without a calculator, just by looking at the equation. And then we're going to graph 2 of them to see how we can use our strategies for graphing. All right, let's see how you did. Did you get 1, 2 for the first one? And -3, 6 for the second one. 4, -7 for the third one. This one's a little tricky because it has a 0. Did you get 0, 5? Excellent. And this one has a 0. Did you get 8, 0? And this one has a 0, -2, 0. And the last one has a vertex at 9, 1. The vertex is undoubtedly the most important point on a parabola. So now, if I look at this very first one, y equals x minus 1 squared plus 2 1, 2, 3, 4. We can graph this quite easily if it's in this form. And this form is called the standard form. Why? Well, I know where my vertex is. So the first thing I can do is I can go to 1, 2, label that. That's going to be my vertex. Even though it's not written here, can you see that your a value is equal to 1? If your a value is equal to 1, it's positive, it's going to open up. And since it's a 1, it's the same shape as a regular x squared graph. And the pattern we saw on a regular x squared graph is you could go over 1, up 1. So that would give me another point in both directions. I could go then over 1, up 3. And that would give me a second point in both directions. And now I have 5 points labeled, which is more than enough to draw your parabola. But since I went over 1, up 1, I would know this point is at 2, 3. And since I went over 1, up 3 from that, I would know that this point is at 3, 6. If you forget the over 1, up 1, over 1, up 3, over 1, up 5, you can always find more points by just plugging in x values. Like, does it check? If I plug 3 in for x, do I get 6? Well, 3 minus 1 is 2. 2 squared is 4. 4 plus 2 is 6. Yes. So you can double check your points that way as well. Or you can add more points just from a table of values. Now we're going to do one with a number in front. Oh, this negative is a good idea. So I know my vertex is at -3, 6. That's way up here. And this time my a value is a -2. So it's going to open down. But instead of going over 1, up 1, I'm going to go over 1, down 2. And then I would go over 1 again, and instead of down 3, I would go down 6, giving me a point here, which would also be a point on that side, a point here, which would also be a point on that side, and there is our parabola. I could label these points. This one's going to be at -2, 4, and this one's going to be at -1, -2. Again, I could double check. If I plug in -2, -2 plus 3 is -2 plus 3 is 1. 1 squared is 1 times 2 times a -2 would be -2 plus 6. Yes, I get 4. And double check them by plugging them in. But the pattern lets you graph it really quickly. So this standard form of the equation lets us graph it quickly. So we can just sort of highlight. If you want to take out your highlighter, we're going to do some highlighting on the next page. And they don't even give you this chart in your notes, so we can ignore it. And we can say the graph, if you have that plus q, and here's a key word for describing it, we call this a vertical translation, because you're taking your regular graph and moving it up and down. The shape stays the same. So if your regular graph of x squared here, right, our regular graph has the over 1, up 1, over 1, up 3, over 1, up 5. Your new graph, after it's moved up 2, still has over 1, up 1, over 1, up 3, over 1, up 5. That pattern stays the same. because it's congruent, it's the same shape as the original graph. If you had a -3, that would move it down 3. Next, what happens with the p-value? Well, we saw that move things left and right. Oh, I want yellow. No. I don't know. I wanted to highlight. Oh my goodness. I deleted the whole page. There's undo. There we go. I just wanted to delete the green. I don't know. I felt like highlighting in yellow first. Keep things consistent. Although I once had a student that was colorblind to yellow highlighter. And so every time I used the yellow highlighter, it looked like I was highlighting it in clear glue or something. Like you can't see it all. So if you can't see that, you might just realize now that you never knew before, you might be colorblind to yellows. And if you are, I can use different highlighter colors. Just let me know. But, okay. So, again, we say the key word here in green is we call this a horizontal translation because you're moving your graph left and right. But still the 1, 3, 5 stays the same. That would stay the same whether you moved it left or moved it right. And then finally, we have the a value in front, and if the a value is bigger than 1, we call it a vertical stretch. If the a value is less than 1, or between 0 and 1, we call it a vertical compression. But we'll also use in this unit narrower and wider. So the graph, if it's bigger than 1, it stretches it vertically, which causes it to become narrower than y equals x squared. And when it's between 0 and 1, it would be wider. So two different ways of talking about it. What I've highlighted in green is more of the language you'll see in the grade 12 pre-calculus. And the idea is they took the original graph and pulled it away from the x-axis, stretching it, which in effect made it narrower. But your brain sees narrower easier than it sees stretching and compressing. So this graph, if someone were to describe it, you're like, yeah, it's wider. Very few people are like, ooh, someone squished it towards the x-axis. But that's technically what's happening. It's getting compressed towards the x-axis, making it wider. And if you have a negative, it flips it, right, and opens down instead of opens up. So on page 278, the last things we're going to highlight. Very important, this is called the standard form, right there. And the standard form is super helpful because with the standard form, you know your vertex exactly where it is at P and Q. And your axis of symmetry is always x equals P, which is the x coordinate of your vertex. Sometimes it opens up, sometimes it opens down, sometimes it's wider, sometimes it's narrower. That all depends on the a value. So what we're going to do is now we're going to use this standard form to help us find equations of graphs and to help us graph. We've already done the graphing in the construct the understanding, how you could use the vertex and then use the a value to find the others. in example 1 here, we have the graph. So we think about the standard formula. And in order to find the equation of this, we have to put in a number for A, for P, and for Q. We need numbers there. We want to find the equation, we need numbers for A, P, and Q. Well, can you see from the graph, you can already tell where the vertex is. If I look at my graph, my vertex here is at, oh, it's going by 2's again, 4, -2. So I could already put in values for P, and if it's 4 to the right, how does that show up in the equation? X minus 4 is always opposite inside. If it's 2 down, that shows up as 2 down. So we have to know that the P value is sort of always the opposite, and the Q value is exactly what you see. Now there's 2 ways that you can find your A value. I'll show you the easy way, but the easy way doesn't always work. The easy way is you go over 1, so I go over 1, and then I'm like, oh, I have to go down, and if this works out to a nice number, you're golden. It doesn't always work out to a nice number. What does it look like I went down? 5? I don't think so. It looks like I hit -5, but how much did I actually go down then? Oh. 3. I would have gone down 3. Double check it. That means if I went over 1, how much should I go down to get to my next one if it follows the pattern? 9, right? Because it's usually 1, 3, 5, but now it's been tripled, so it should be 3, 9, 15. If I go from -5 to -14, it matches up. So this is one that it would work that you could use the shortcut and say, I went over 1 down 3, so my A value is -3. That doesn't always work. So you have to know the following technique for how to solve for A. So we had this. We knew our vertex, so we could put in P and we could put in Q, but we didn't know A. And you'll have to use this technique because sometimes your A value might be a fraction like 7/13. And no amount of looking at your graph will help you figure out that number. You'll be guessing and you'll be like, I don't know. Close to a half? And then you find out, no, it doesn't. So this is the algebraic way to solve for A. It's a beautiful method. The idea is as follows. If you know a point on your graph and you're like, oh, they labeled a point right here. That point is at 2, -14. Any point on the graph other than the vertex. You know any point on the graph other than the vertex. An equation of a graph says if a point is on the graph, it makes the equation true. If a point is off the graph, like that will not make the equation true. It's definitely not on the graph. So it won't make it equal. But if a point is on the graph, it makes the equation true, which allows you to say, I know that when y is -14, that x has to be 2. And if I plug in my point, which has to be true, well then I have an equation where the only thing I don't know is A. Do I have like terms? Yes, I could add 2 to this side. Those are like terms. I could do the math here. 2 minus 4 is -2, and a -2 squared would be 4, so this becomes 4A. If I divide both sides by 4, I would get A is equal to -3. And if you did it this way, your next step would be now finally write your equation, because you needed a value for A. We just figured it out. We had P and Q. So our goal is to find a number for each of those, and once you've done that, this is your final equation. Okay, circle questions 3, 4, and 7.